In this episode, we look at several design ideas that help systems stay available when individual parts fail or demand suddenly changes. You will hear terms like platform diversity, load balancing, clustering, autoscaling, high availability, and multi-cloud resilience. These ideas are related because they all try to reduce dependence on one fragile piece of technology. A single server can fail. A single application instance can crash. A single provider can have an outage. A single hardware model can have the same defect across many systems. A single configuration mistake can spread across an environment. Resilience design asks what happens when something breaks and whether the service can continue anyway. The goal is not to pretend failure will never happen. The goal is to design systems so that failure is expected, contained, detected, and handled with as little disruption as possible for the people and business processes that depend on the service. Before we continue, a quick note. This audio course is part of our companion study series. The first book is a detailed study guide that explains the exam and helps you prepare for it with confidence. The second is a Kindle-only ebook with 1,000 flashcards you can use on your mobile device or Kindle for quick review. You can find both at Cyber.Me in the Bare Metal Study Guide series. A single point of failure is any one component that can bring down a larger service if it stops working. That component might be a server, database, storage device, network connection, firewall, power supply, application process, cloud region, or identity service. The phrase is simple, but the idea is central to resilience. If one thing fails and everything stops, the design is fragile. If one thing fails and another part can continue the work, the design is more resilient. Removing single points of failure usually means adding redundancy, alternate paths, failover options, monitoring, and tested procedures. It also means understanding which systems are important enough to justify the extra cost. Not every small internal tool needs an elaborate design, but important business services often do. When you read a scenario, look for whether the organization is trying to keep a service running despite failure, increased demand, or maintenance. Platform diversity means using different platforms, technologies, vendors, operating systems, hardware types, cloud environments, or software stacks, so one shared weakness does not affect everything at once. If every critical service runs on the same operating system version, the same hardware model, the same virtualization platform, and the same cloud provider, one flaw or outage may create a widespread problem. Diversity can reduce that risk by avoiding complete dependence on one platform. For example, an organization might run critical applications across more than one type of server, more than one availability zone, or more than one cloud service provider. The benefit is that a failure in one platform may not automatically stop every service. The trade-off is complexity. Different platforms require different skills, monitoring methods, patching processes, licensing models, and troubleshooting habits. Platform diversity can improve resilience, but it also creates more moving parts to manage carefully. Platform diversity is not the same as random variety. Adding different technologies without a clear reason can make an environment harder to secure and harder to recover. A good diversity strategy is deliberate. It asks which shared failure would cause the most harm and which differences would actually reduce that risk. For example, using two different cloud regions from the same provider may help with a regional outage, but it may not help if the provider's identity system has a broad failure. Using two different providers may reduce provider dependence, but it may also complicate network design, logging, access control, billing, and incident response. Diversity also affects staff readiness. A team that understands one platform deeply may struggle if an emergency requires them to operate a second platform they rarely use. The security lesson is that diversity should be matched with documentation, training, monitoring, and testing so it strengthens resilience instead of becoming unmanaged complexity. Load balancing distributes traffic or work across multiple systems instead of sending everything to one place. If an application has several servers available, a load balancer can direct incoming requests among them. This helps with performance because no single server has to handle all demand. It also helps with availability because traffic can be shifted away from a system that is unhealthy or overloaded. You can picture a busy store with several checkout lanes. If one lane closes, customers can move to another lane instead of the entire store stopping. In technology terms, The load balancer acts as a traffic director. It may consider server health, connection counts, response time, location, session needs, or other rules. The important point is that load balancing makes the service less dependent on one application instance. It does not remove every risk, but it helps spread work and supports continuity when individual backend systems have problems. Health checks are a key part of load balancing because the load balancer needs to know which systems are ready to receive traffic. A basic check may confirm that a server is reachable. A better check may confirm that the application is responding properly, the required service is running, and the system can actually handle requests. If a server stops passing health checks, the load balancer can stop sending it new traffic. When the server recovers, it may be added back into rotation. This process can reduce user impact because failed systems are quietly removed from the path. Load balancing can also support maintenance because administrators may drain traffic from one system, update it, test it, and then return it to service while other systems continue handling requests. The limitation is that the load balancer itself must also be resilient. If the load balancer is a single unprotected device, it can become the new single point of failure. Clustering connects multiple systems so they work together as a coordinated group. A cluster may be designed for availability, performance, or both. In an availability-focused cluster, one node may take over when another node fails. In a performance-focused cluster, several nodes may share processing work at the same time. Clustering is common in databases, application platforms, virtualization environments, and storage systems. The value is that the service is not tied to one machine. If one member of the cluster has a problem, another member may continue supporting the service. Clusters often require shared configuration, heartbeat communication, data replication, quorum rules, and careful failover behavior. Those details can become technical quickly, but the beginner-level idea is straightforward. A cluster is a group acting together so the workload can survive failure or scale beyond one system. It is stronger than one standalone server, but it must be designed and tested well. Clustering also introduces its own risks because coordinated systems must agree about state, ownership, and timing. If two cluster nodes both believe they are in charge at the same time, data corruption or inconsistent service behavior can occur. If the network connection between nodes fails, the systems may not know whether a partner is down or simply unreachable. If data replication falls behind, a failover may bring the service back online with missing or outdated information. This is why clustering is not magic. It requires planning for how nodes communicate, how decisions are made, how data stays consistent, and what happens during partial failures. For exam purposes, you do not need to configure a cluster, but you should recognize the trade-off. Clustering can improve availability and performance, but it can also add configuration complexity, synchronization challenges, and new failure modes if it is not managed carefully. Autoscaling adjusts the amount of computing capacity based on demand or defined conditions. Instead of keeping the same number of application instances running all the time, an environment can add capacity when traffic increases and reduce capacity when traffic drops. This is common in cloud and virtualized environments because new instances can often be created faster than traditional physical servers could be purchased and installed. Autoscaling helps availability because a sudden increase in users does not have to overwhelm a fixed set of systems. It can also help control cost because the organization may not need to pay for maximum capacity at all times. Autoscaling depends on good monitoring signals. Those signals might include processor use, memory pressure, request volume, queue length, or response time. If the signals are poorly chosen, scaling may happen too late, too often, or not at all when the service needs help. Autoscaling can make an environment more resilient, but it also requires discipline. New instances must start with secure configurations, correct patches, approved images, proper logging, and the right access controls. If autoscaling rapidly creates vulnerable or misconfigured systems, the organization may increase capacity while also increasing risk. The application must also be designed to handle scaling. If every new application instance depends on one overloaded database, adding more application servers may not solve the real bottleneck. Session handling, storage, licensing, network limits, and dependency capacity all matter. scaling the front end while ignoring the back end may simply move the failure point. You should think of auto-scaling as elastic capacity, not automatic resilience in every possible situation. It helps when demand changes, but it works best when the entire service architecture is built to expand and contract safely. High availability means designing a system or service to remain accessible with minimal interruption. It often uses redundancy, failover, monitoring, clustering, load balancing, diverse paths, and careful maintenance practices. High availability does not mean nothing ever fails. It means the design tries to prevent one failure from becoming a full outage. A highly available service may have multiple application instances, redundant databases, more than one network path, backup power, replicated storage, and automated detection of unhealthy components. The goal is to reduce downtime and make recovery faster when problems occur. High availability is often measured against business expectations. A system that supports emergency response, financial transactions, online ordering, or identity services may need a much higher availability target than a system used only for occasional internal reporting. The more important the service is, the more carefully the organization has to design, test, and monitor its availability. Multi-cloud resilience means using more than one cloud provider as part of a resilience strategy. The basic idea is that a failure, outage, policy change, account issue, or regional problem at one provider does not automatically stop everything. A multi-cloud design may place different workloads in different clouds, keep standby capacity in another cloud, replicate certain data across providers, or use one cloud for primary service and another for recovery. This can reduce provider dependence, but it is not simple. Each provider has its own identity model, networking approach, security tools, storage services, monitoring options, and cost structure. Moving an application between clouds may require design changes. Data transfer can be expensive and slow. Staff may need skills in more than one environment. Multi-cloud can improve resilience when it is carefully planned, but it can create confusion and security gaps when it is adopted without clear architecture and governance. All these resilience designs add complexity, and complexity has to be managed. More systems mean more things to monitor, patch, document, configure, and test. More providers mean more contracts, more dashboards, more identity relationships, and more places where data may exist. More automation means more reliance on policies, templates, and monitoring rules being correct. A highly available design can still fail if nobody notices that one redundant component has been broken for months. A multi-cloud design can still fail if the recovery environment has not been tested with real dependencies. A load-balanced application can still fail if every server depends on the same exhausted database. Good resilience planning includes observability, alerting, change management, configuration control, incident response, and regular exercises. The design should not only look resilient in a diagram. It should be understandable and maintainable by the people responsible for keeping it alive. Security also has to remain consistent across resilient designs. If one platform has strong identity controls and another has weak ones, attackers may target the weaker environment. If load-balanced systems are created from different images, some may be patched while others are not. If auto-scaled instances do not send logs to the central monitoring system, incidents may be missed. If a standby environment has old credentials or outdated configurations, it may become a hidden risk. Resilience should not create a second-class environment where security standards are lower. The same principles still apply, including least privilege, secure configuration, encryption, logging, vulnerability management, and access review. This is especially important during emergencies because teams may be tempted to bypass normal controls to restore service quickly. A good high availability or recovery design allows operations to continue without abandoning security discipline at the moment it is most needed. For security plus questions, match each term to the problem it solves. If the scenario describes spreading traffic across multiple servers, think load balancing. If it describes a group of systems working together so another node can continue service after a failure, think clustering. If it describes automatically adding or removing capacity based on demand, think autoscaling. If it describes reducing dependence on one vendor, operating system, cloud, or hardware platform, think platform diversity. If it describes keeping a service running with minimal interruption through redundancy and failover, think high availability. If it describes using more than one cloud provider to reduce provider-specific outage risk, think multi-cloud resilience. Also watch for the downside. The exam may ask for the risk introduced by these designs, and the answer is often complexity, inconsistent configuration, increased management burden, higher cost, or the need for careful testing. The larger lesson is that resilient systems are built with failure in mind. Platform diversity reduces the chance that one shared weakness affects everything. Load balancing spreads work and helps route around unhealthy systems. Clustering allows multiple nodes to support a shared service. Autoscaling adjusts capacity when demand changes. High availability combines redundancy, monitoring, and failover so important services can keep running. Multi-cloud resilience can reduce dependence on one cloud provider, but it also adds operational and security complexity. These designs are powerful because they give organizations options when something goes wrong. They are not free, and they are not automatic. They require planning, consistent security, clear ownership, and regular testing. When you understand both the benefit and the trade-off, you can choose the design that fits the scenario instead of assuming the most advanced-sounding option is always the best answer.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.